should be is it's the parent node plus the distance we had to travel to get to this new node. So the problem there is that in a grid cell, what I've told you is in a grid cell, we assume a distance of 1. However, in Unity, that's not the case. Your grid size, which you used in the last assignment, is 0.2. That's the issue.
No, not at least
Hello, Zoom crew.
You literally just implement these stuff. I don't know. I haven't looked at it.
And Manhattan is good for grid-based movement.
Yeah, but it's good for non-diagonal movements. But
Correct.
this one, the assignment is non-diagonal movements.
Right.
So Manhattan
It's pretty good.
Yeah, so how to improve it?
Well, so the key for a good heuristic, right, is you want it to be as close as possible to the true cost of getting to somewhere without going over that, right? So if we think about it, right, we talked about this a little bit, right, when we were first talking about heuristics of saying, if we're in an environment, for example, that has obstacles, right? If I just do a straight line distance to my goal that's through an obstacle, that's not accurate because I'm going to have to actually go around the obstacle, right? So this is one example of where a straight line distance is not a very good heuristic. And there's ways, because you can access obstacles, right? I give a hint in the PDF, this is not new, of me saying you can access obstacles. Because you can do that, there's extra stuff you could do in terms of figuring out like, hey, how much really is it going to take for us to get around this obstacle if there's an obstacle in the way? Does that make sense? That's about all I can give you because that's the stuff that's already in the assignment PDF. If you have particular questions about the credit, I'm happy to answer them, but otherwise I can't, give you more guidance than that because it's the extra credit.
And then the Thursday, actually the middle of Friday.
Yeah, because tomorrow is a holiday. Yeah. Okay, let's go ahead and get started. So today we are covering trees and Monte Carlo tree search. But really, this is the lecture which is going to move us from talking about path planning to decision making. So we're going to move from just moving in virtual spaces to acting in virtual spaces. We're missing a lot of people today. Oh, I guess because Monday was the quiz review and people really wanted to see that. People don't care so much about this stuff. That makes sense. Okay, so some quick announcements. Homework 2, assignment 2 is due Monday. I have the same late policy again. So you have that 23-hour late policy, my brain is just not working today, grace period, where you can just submit and it doesn't matter. If you need more time than that, reach out to me. And we can work that out. On Thursday, speaking of, tomorrow is the Orange Shirt Day / National Day of Truth and Reconciliation. If you didn't already figure this out, there's no classes tomorrow. So if you were thinking at this point you had to come up and show up to lectures tomorrow, you do not. This is why our help period is gone from Thursday to Friday. I have to move it to 5:15 as a start time because otherwise I wouldn't be able to make it somewhere where I could host for 3 hours because I'm gonna have to walk home. I also still have my 12 to 1 p.m. office hour. By the way, this came up because the majority of you voted for Friday. Otherwise, I would have been happy to have it today. Sorry for the 33.9% of you who wanted it to be Wednesday, but what can you do? This is democracy. speaking of, Thursday, we have the National Day of Truth and Reconciliation, aka Orange Shirt Day. And I normally would do this on that day, but I'm not lecturing on the day because there's no lectures on that day. So you might say like, hey, why does the Orange Shirt Day matter to games? It turns out games are like extremely bad at dealing with Indigenous subject matters. So like, let's look at some examples here. Horizon Zero Dawn, if you're familiar with that one, just totally cribbed a whole bunch of Indigenous people's designs without any reference to Indigenous peoples of America. Over here, we have Infamous Second Son. Did anybody play Infamous Second Son? No, okay, understandable. It was a PS4 launch title and it wasn't very good. But rather than actually make use of like the real Indigenous tribe that was in the area where the game is placed, this is Suquamish, they created a fake one for some reason and just like stole everything about them. They just didn't want to actually engage with like the real people that live there. And perhaps worse is This Land Is My Land. Has anybody heard of this one from 2020? Got a little bit of buzz on Twitter because it's so bad. It's basically a terrible Assassin's Creed ripoff made by a whole bunch of white people you're playing as like a vague quote unquote Native American who's like killing settlers, but with no notion of like what people is this person from, like what's going on culturally here. It's just like a murder frenzy. So not great, right? Yeah, what's up?
Apparently, Zoom can't see the slides.
Oh, Zoom can't see the slides. Oh, that's because I didn't share the slides. Instead, you just got a podcast for a little bit, Zoom. Yeah, thank you. Let's try that again. Oh, this is not going to work if I do it that way. Give me one sec. Yeah, and there's all the messages saying, hey, what's up? It was a great podcast. I'm so glad. Anyway, I'm not going to talk about this for more than just a single slide, but if you're interested, I have like a further link where you can follow up on all the nasty stuff going on over there. So, hey, in games, we can do better on these topics too. So worth talking about that a bit. All right, so last time, in addition to the quiz review, I did some quiz polling and I wanted to talk about the results of that. So first of all, this was when there was 59 responses. I think there's like 64. I'll be closing this after this lecture. So I would recommend doing it if you haven't done it yet, because there's 88 people enrolled in the class and that's not close to 88. But this is sort of a breakdown. I don't like pie charts, but it's what Google Forms produces, where about 69.5% of you said it was about what you expected, which is pretty nice. And only about 20% said it was harder, and this collectively is easier and much easier. That's about 10% of you. And I'm honestly pretty okay with that as a setup. I think that having around 70% of you saying it was about what you expected is pretty good. And if 10% say it's like easier, much easier, like, hey, this is supposed to be a second year course. Yeah, some of you are going to find it easier. There's not much I can do about that. There were some comments, and I wanted to address some of those. First of all, there was a whole bunch of really nice comments, and I do appreciate them, but I'm not going to talk about them because it's just not worth talking about in class. So some questions. So for example, steering behaviors are still confusing. Is all steering made up only of examples shown in class? No, right? We talked about how in the Sunset Overdrive, there was examples of steering we didn't cover in class. And I said you could invent new steering methods. All that steering is a secondary post-processing that we do after we have a path or after we have a place that we're trying to get to. That's it. It's some kind of secondary thing that's happening. That's all. There's also a whole bunch of comments on like the content of the quiz or the style of the quiz. So this person said, I feel it wasn't at the difficulty where I really was forced to understand the material. I could just go check the notes for answers to all the questions. They went on to say like they would have preferred that, it was just like a 1 hour time period. So a few things, and I think there was actually this next one as well. No, this is just about the confusingness. So a couple things on this. The quiz was designed to be a 1 hour quiz, but that's with the assumption that you studied ahead of time. Now I can't make you study ahead of time, right? And it's not in class forcing you to study ahead of time, but this is how it's designed. Now you might say, hey, why am I not just having it in class? Well, we have a whole bunch of people who literally can't come to class, either for health reasons or because they're not on the continent. So that would be tricky. So we can't have it in class. And you could say, okay, well then let's have it online at a particular time. Well, we can't do that for the same reason of we have some people who have to wake up in the middle of the night. So that's the reason for this setup that I'm going with this semester. It's not ideal. I recognize it's not ideal, but this is what I meant at the start of the semester when I said, you just have to be patient with me and understanding of like, this is weird conditions that we're under. But if you're finding that you're sort of relating to this of like, hey, I would really have preferred if I like had to actually look at the material ahead of time. I couldn't just check my notes. Like, you're adults. Like, you could do that if you wanted to, right? Hold yourself to that. You can always check it afterwards by looking at your notes. Anyway, I had 3 different questions, comments rather, saying that some of the question wording was confusing. Part of this is intentional, right? Part of the way that I design quizzes is that there's some ambiguity, and addressing that ambiguity is important. I wanted to say 2 things to this. One is you can always state in your answer to the question, hey, I'm assuming this meant this, right? And I won't take off points as long as that is a reasonable assumption to make. But you can also literally send me a message. If it's unintentional that something is ambiguous, I will just say, hey, this is what I meant. Like for the listing the current nodes questions, where a whole bunch of people thought I wanted numbers. I was just able to say, hey, I want letters here, right? So you can always ask if you're confused about something. Oh, this is just a similar kind of comment, right? About saying that they were more likely to spend 2.5 hours writing the quiz by referencing notes. Like, this is up to you, right? This is on you. I'm not going to force you to take 1 hour. You can do it if you want to, but you don't have to. Finally, it was too easy, or not finally, sorry, there's one more that's very funny. It was too easy to be a 48-hour open book quiz. The difficulty would have been right if it was in class, closed book, and 1 hour long. So same sort of comment here along those lines. And then finally, an hour felt too short, a recommendation time to do the quiz. So, you know, you can't please everybody. There's a lot of people, you're all very different people. You're gonna come at this with different expectations, different needs. I'm gonna do my best to address all of those, but I'm not gonna be able to address everybody's needs. I just ask for your patience. Okay. All right, no other chat. Let's move on. Today, let's get back into topics. So this is our last sort of path planning lecture. So let's do a little bit of a discussion about how path planning works right here at the end to sort of get us into it. So let's say that I want to go from A to H, right? That's my goal. Now, if I were to do this in a greedy fashion, I would end up exploring this route, basically. I would basically end up continuously picking as my current node, the node that was in my open set and closest to the actual node, which would mean that I would just end up basically straight line distancing there. Now, if this was A star instead, I would do a sort of a broader view where I would end up picking everything that had the same F score potentially before I moved on. So this is actually kind of interesting because this relates to 2 different ways of doing tree search. Does anybody know what I'm talking about? Yeah.
It's similar to like find a tree search tree where you like explore different nodes.
Not quite. It's 2 different ways of exhaustively searching a tree. Yeah. Yeah. So over here on the left, right? That's depth first search. We're going straight down as quickly as we can. Over here on the right, that's breadth first search, right? We're searching everything at 1 level before we search further. The difference here is that these aren't trees, right? But before I get too deep, let me explain what I mean by trees, because many of you are not going to be familiar with what a tree is. So a tree is a kind of directed graph. We're going to assume all the edges are going to go one way. That's what it means to be a directed graph. There's a couple other things going on here as well, right? We have to have a root node. That's, I don't know why we just called it a tree. If you turn it upside down, it looks like a tree. It basically looks like a root system. I don't know why computing scientists way back in the past did this. Don't ask me, but it's a tree. That's what it's called. You're going from a single root node, as I mentioned, and it allows us to make certain assumptions. Like generally, you don't have any loops, right? So we don't go backwards. We don't ever need to go back again. And they can look like all kinds of different things, right? So like we could start from one point and then go outwards from there. We could, you know, if you flip it upside down, you could go up like that, and that looks quite a bit like a tree. But this is a much more typical way of looking like a tree. So in those examples that I was just showing you, right, of A star and greedy, what's functionally happening here is they're building a tree as they search. This can be a little bit tricky to visualize, and I'll show you an example of it in just a second, right? But basically, we're building up this tree as we sort of explore this graph. Because we're starting at one place and we're not going back to the same place ever again, right? Let me show you in this in a little bit easier way to visualize. So if we have this graph, right? This grid over here on the left, If we run A star, or AKA breadth first search, then we can get a tree like this, right? If say if we're going from, I should specify, if we're going from like B to L. So if we're going from B to L, obviously we start at B. From B, we can explore A, F, and C. From A, F, and C, we can explore E, J, B, and D. I'm using depth for here, D, but this could just as equally be your G score value, right? Your G score value at B is 0, your G score value at A, F, and C is 1, 2, etc. Does that make sense? Seeing some nods, but some confused faces. Any questions on this? High-level idea is just that you can re-represent our graph, because we already talked about how all these things can be represented as graphs, as trees, by having a particular starting location and exploring from there. This is going to become important in just a sec. Let me give you another example, right? This is the same path network that I was showing you before, and here's what it would look like. The trick is that it's the same tree. I just changed the graph representation on the left, but it's the exact same tree, right? So this is interesting, right? Because it means that we can actually compare these two different environments that look very different based on their trees. Based on the trees of going to these similar kinds of points between them. In this case, they're exactly the same. Okay, let's make sure you understand this. First question. That's right, we're starting off fast. Give me the nodes at each depth of the tree, starting at node A with BFS/A star. Just assume that you're trying to go as far away as possible, right? The hint here is that max depth is going to be equal to 3. You're basically just going to fill in each. Whoa, I don't know what that was. Mirostella says, why is A star used alternatively with BFS? Because in the case where we are exploring everything with the same F square value before moving on, A star is equivalent to BFS. Throw this link into there and also write it out on the Discord. Let me move the chat. Get out of here, chat.
Professor, for the, hello, can you hear me?
I open up Discord on my laptop, but I don't trust my friends not to be smack talking me in Polytopia. Yeah, I play Polytopia. Yeah. Oh, it's not set up? What does that mean? I'm pretty sure it's set up.
Last 3 questions. Right.
That's funny. We're going to fix it live. Yeah, just click option 1 each time. Easy. I mean, you can. I'm not going to stop you from clicking option 1 each time. Let's try that one more again. Probably don't actually need the paragraph. You should be able to retweet and it should be fine. Retweet. Should be able to refresh. Yeah, option 1's good. Okay, since since that got a little bit mucked up, let's just go ahead and go through the answer. We also don't have a heck of a lot of time today. So basically it looks like this, right? Assuming that we're going to have no repeats, assuming that we're trying to go as far away as we can, which in this case is H, right? Then we've got to start at A. From there, we can go to C, B, G, and F, and K. There's a direct link to K, and then so on and so forth, right? I'm not going to stay on that, so you can just copy the answer. I'm sorry for those of you who wanted that. Okay, so let's talk about why I'm talking about trees at all. Yeah, well, we talked about before that A star is good for dynamic small environments, right? And we talked about that APSP is good for static small environments. But what do we do about big environments or big dynamic environments, right? I mentioned when I was going over, hey, here's a situation, what path planning approach you would use, that we would use specialized use cases for these sort of larger environments. And in this case, we're going to talk about one of them, which is Monte Carlo tree search. Has somebody heard about Monte Carlo tree search before? Okay, all right, yeah, about 6 hands, mostly shaking heads. Question 3, I'm talking about question 2. I have no idea what they're talking about. Okay, so in a large dynamic environment, basically we cannot necessarily compute distances quickly, right? because the environment is constantly changing. And so we don't necessarily want to take the time to like do a full A-star pathing all the way to the end, right? Because the path that we need to take might change as we're taking. So that's not great. So rather than doing that, we can randomly simulate out a potential path of fixed length L very quickly, right? If we just say from a given starting point, we're going to randomly take L actions, L movements. We can do that extremely fast, right? Secondly, it's O of 1, but I'm putting here O of L. This is called a rollout, right? We're going to do a random rollout in terms of taking random actions and just see where we get. Basically, the idea here is that we want to simulate as many rollouts as you can with a limited computation time, and then take whatever path is best based on what we've found. High-level intuition. Does that sort of make sense? Okay, so let's talk about some steps to this. This is the extremely standard MCTS figure, but I'm going to use this to sort of talk about it initially, and then we'll sort of dive into it a little bit more. So selection. In selection, what we're doing is we're going to go from our root node, right? And we are going to select, well, in this case, it's actually any node, but we're going to select a sequence of nodes, right? Until we hit whatever our maximum rollout length is. If at any point during the sequence of doing this rollout, we get to a node we haven't before, this is a little bit confusing for some people. So this is the same kind of notion of we're building up the tree as we do the search, as I was showing you earlier with greedy and A-star. So the graph, the full graph of the world exists, but we haven't necessarily represented it in our tree yet, okay, the particular nodes. So when we've gotten to a node that we haven't seen yet while doing the search, we add it to the tree. Does that make sense? Cool. Then if we hit the end of our rollout, then at that point we need to simulate what's going to happen from there. So simulation is a very complex way of saying when we're just doing path planning, all we're going to do is do a heuristic from that. So we're going to say, wherever we got, far we got, let's just use our heuristic at that point to say how much further we expect it to be. Now, in certain situations, the reason why it's called simulation is that it gets a little bit more complicated than that, but we'll talk about that in a bit. Then the last step is back propagation. For those of you who've had some interest in deep learning, you might hear that term and go, ooh, back propagation. It's not exactly the same thing. It's the same kind of idea, but it's not exactly the same thing as with deep neural networks. Okay, so those are the major steps. Let's talk about those in a little bit more detail. So for selection, right, we're going to do this rollout of length L. We're going to follow some tree policy. This is a fancy way of saying, hey, how do we actually pick which of our options of where we should go next, of what we should pick next? There's some common ones, so like random, which is just pick a random thing, pretty straightforward. It could be authored, so it's just say, oh, do this sometimes and do this other times. Like a very standard one is to say, pick the one that seems to be the best, and then randomness with sometime, or it's called epsilon greedy, or it's one way of doing a combination of those things. We'll talk about those things later. And then finally, you can also have a learned strategy for moving through space. But that's not very common in games. Typically, it's one of the first two. Then expansion, if we don't have a pre-authored tree, add each node to the tree as we encounter it, right? That's pretty straightforward, nothing more complicated there. Simulation, either literally play our pathfind from here or approximate the cost of pathfinding from here. Note that I'm saying play. Case of that in a moment. And then finally, backprop. Whatever the cost reward of the final node, we're going to backpropagate that all the way to the very first edge. So let's do a quick demonstration. Let's see. I'm hoping that I can just do this on the whiteboard because getting out my iPad is going to be tricky. So people on Zoom, just yell at me if you can't see, okay? Let's move this even further. I'm just going to use this tiny little corner of the board. Perfect. Okay. Was that mine? No, this isn't mine. Well, we use it. Okay, so let's say that we're trying to get from B to L, okay? And then I'm going to assume that my rollout length is just 2. All right, I'm also going to assume that my tree policy is random. I'm just going to do a random policy every time, but mostly because that's going to let me do whatever I want here. So let's say we're going to start at B. Ooh, this is not a good marker. I'm going to use my actual marker. So we start at B, and then just at random, we happen to go CD. Okay, that was our rollout. We went randomly to C, and then randomly to D. In fact, we could only go to D because that was our only option. So C, oh, so much better, to D. Can you see that okay, people on the Zoom? Yeah, it seems like it's mostly coming through. Okay. So at this point, we've hit the end of our rollout, right? I've expanded twice. I didn't show you it, but I had to expand twice to say that this is new parts of the tree that I'm adding up these nodes, right? And from here, we need to do our simulation. We need to actually figure out, hey, what do we think the cost of going from here is going to be? And then we need to do finally a backprop. So for simulation, let's say that I'm just doing Manhattan distance because it's easy, and that would be 1, 2, okay, in terms of Manhattan distance. So we're going to say this is a heuristic of 2. And then what we need to do is we need to back propagate that back up to our very first node, or in fact, the edge of the very first node, because what we care about ultimately is where do I go next? So what we're going to do is we're going to back propagate that to here. We're going to say we're expecting that this is sort of a too good move to make. That we want lower is better in this case, or so maybe it's sort of like the too worse move to make. And then in terms of back propagating it back up to the start, it's a typical thing to do to have some kind of discount factor, which is just basically a multiple under 1 that we're going to multiply things by, just to make sure that it's not, summing to infinity or something like that. So I'm just going to say that our discount factor is 0.5. I'm representing here as gamma. Don't worry about it. And then this would make this 1 good to do. Actually, no, hold on. In this case, I'm minimizing the opposite of that. You know what? We're just going to keep it at 1. I don't want to have to do math. You're not here to see me do math. So we're just going to say this is 2 as well. Sorry, you can tell that I'm doing this live. So that means that this is now saying this is a too good move, and we're always looking for the best possible move. So then let's do another rollout. So we're going to do the B to F to J, right? So B to F to J. And what do you know? This is going to have a slightly worse simulation. 1, 2, 3 is the cost of this one. So H equals 3, 3, and 3. Let's do this again, but let's go in a slightly different direction. So let's say if we did B, F to E, right? So B, F to E. Now in this case, E is 1, 2, 3, 4 off, right? Not very good. I think a couple of times I was going to H, but I was supposed to be going to L the whole time. Let's just keep going to H, let's be fair. So ignore that. We're saying that we're going to keep going to H. 1, 2, 3. So exactly the same. So that was useless. Why did I do that? There's a reason why I set it up to be H. It's fine. So that would be 3 as well. 3 as well. Now we have a situation where we have 2 different values that should be on this edge as we're backdropping and getting back up. A typical thing here is to take like an average over the values or something like that. Guess what? That means this stays 3. I really should have gone to L. If I'd been going to L, this would have been 5 this time, right? And we would have had to take an average and it would have changed our predictions, right? At the end of this process, I'm going to end up picking the edge to go on next that has the minimum cost in this case. So in this case, that would be going to C. This is wrong. This is not the right thing. Oh, this is the right thing. I thought I'm going to H, but I was supposed to be going to L. You know how it is. So if I'm going to C, hey, that's correct. We're totally fine. But if I was going to L, this would entirely be the wrong thing to do. Okay? So this is not to say this is a perfect approach, but you can generally sort of build up this estimation as you're going. The key here, the key thing to take away from this, besides the fact that I just can't read the letter L apparently, is that we're not actually going to do the entire pathing all the way every time. Right? We're not going all the way to H. We're just trying to figure out in this very next step, where do I go next? Okay. I don't have a full plan. Not like with A star, where I have a literal, hey, I'm going to do this, then this, then this. For just this next iteration, this is going to be where I'm trying to go. And on the next frame, I'm going to keep on updating this process. I'm going to keep on doing rollouts for as much computation time as I have to update my prediction. And I'm not going to throw away this tree. This tree is going to stay. So do something like this. So if I end up going to C, I'm going to retain this part of the tree. I throw away the rest of it because I don't need it anymore. Or sometimes you don't because you need to backtrack. But depending on your implementation, you could just throw it away. We can retain the rest of this. So if I had more options in terms of ways to get to H, then if there's more graph over here, then I would retain all that computation that I did earlier until it's no longer valid because a path gets cut off or something like that. So in this way, we get sort of the benefits of APSP, right? We're sort of not throwing away computation. We're keeping our computation as long as we can, but with the sort of dynamic situations of A star. Does it make sense? Cool. Okay. Oh, geez, it's already so late. All right, so where is this used? Well, it's used in situations where we have very large maps and a lot of units, and they're very dynamic. So things like real-time strategy games, it's the most common. Why does this make sense? Well, it's because you don't actually know if you're going to be able to do a path all the way to the end. And so it doesn't make sense to plan any further than a few steps ahead. Does it make sense? Okay. Okay. Now the change happens. Now the twist happens. Automated game playing. So this is having an AI agent actually try to play a game. All right. Many of you, when you heard game AI, you were probably assuming this was everything we were going to talk about. But now we're finally talking about it. Who knows what this is, this image here? Oh, geez, nobody? Yeah, he seems confident. Oh, you're not, okay. Yeah, so this is Deep Blue versus Kasparov. Now that those words have been said, does anybody else know what this is? Oh my, okay, so nods, thank goodness. All right. Geez, I was about to be like, oh man, I'm so out of touch. So this was an early example of an AI beating a human. One of the largest, most public examples of an AI beating a human at a game. This is Gary Kasparov over here on the right, head and hands. And he's just being beat by Deep Blue, which is a computer which is built by IBM. This approach, approach, Deep Blue, relied on a simplified version of MCTS. Okay, who knows this one? Yeah, but you.
It was AlphaGo, and I forget who they were going against.
Lee Sedol, yeah. Okay, so this one a lot more hands shot up. This is a lot more recent, so it's understandable that people will be more familiar with this. It's the AI beating chess. Yes, Deep Blue is before DeepMind. Deep Blue is far before DeepMind, significantly before DeepMind. AlphaGo, yes. So this is AlphaGo versus Lee Sedol. So this was Google, not IBM, but exactly the same thing happening. And also, believe it or not, reliant on MCTS. Now they also had, deep neural networks and things like that, but also made use of MCTS. So here's your second question. How could we use MCTS to do automated game playing, for example, for chess? Oops, I almost jumped to the answer. Don't do that, Matthew. There's a confusing thing here with the participation questions where this is 11B and the last one was 12. This might give you a hint as to why the last one had option 1 as every single thing. Hopefully I didn't just put option 1 1,000 times here as well. I don't think I did because there's only one question. All right. Okay, you've had a couple of minutes. Does anybody who hasn't spoken yet this class want to give me an answer? Doesn't have to be right. I'm just looking for ideas here. People on the chat count as well. I think my Zoom camera shut off again. I don't know why it keeps doing that. No, nobody? Yeah, please. So not a node, but each edge, right? Each node would be a board configuration. Each edge would be a move of player, right? Does this distinction make sense? Yeah, you got it, right? For those of you who've already taken search-based classes, who've already familiar with MCTS, this was probably extremely trivial. But for those who haven't, right, the basic idea is that we want to treat each board position as a node, and then treat each move as an edge to another board, right? We're still sort of dealing with movement, but instead of being a movement in a literal sort of representative space, we're talking about the movement of pieces, of moves in a game, right? And then at the end, when we want to do our simulation step, we need to evaluate our boards based on some heuristic. So for example, in chess, you might do things like the number of pieces that each side has, right? Or some other measurements in terms of how far away do we think we are from a check or a checkmate. Or if you're more familiar with non-chess, right, think of this as any game, where if this is a competitive game, two players versus each other, we could use the score difference between the two of them as a heuristic to say how good do we think this final state we got to was. Does this make sense? So this is our first time, your first time in this class, where we've talked about a way where you can actually have AI doing things, doing actions, not just moving. And it's based on the same concepts that you've seen so far. In fact, we're going to jump back around in a few weeks, and we're going to talk about how A* can be used to guide AI actions. But for now, we're just talking about MCTS. So let's look at super simple example. And by super simple, I mean it still doesn't fit on a slide. But this is a simple, relatively simple example for tic-tac-toe, which is small enough that I can mostly represent it. Right? So from an initial configuration, in this case, it's very hard to see for those of you who are here, but it's XX along the top and then OO sort of on the second row. We can say, here's all the different moves that people can make, and so on and so on and so forth. This is actually alpha beta search, but it's the exact same tree as it would be for MCTS. Does this help in terms of visualization for how you can think about a tree as a state of states instead of game states? All right. So at this point, you might be thinking, oh man, MCTS sounds great. Everybody's got to be using it all the time, right? For all enemy AI. It's actually very minimal. Anybody have any ideas about why you actually generally wouldn't want to make use of this for enemy AI? I literally just told you, like, it's so good. It beats like world champions. Yeah.
It takes a lot of computational power.
That's one of the reasons. That's one of the reasons for sure. It's expensive if you want to have good moves, right? IBM made Deep Blue and had it go up against Kasparov because they were primarily trying to advertise about how good their computing was. Hey, we can run this huge amount of computation. Hire us, right? Any other ideas? Sorry, can you say that again? The runtime is slow, so that's related for sure, right? So unless we had like a very powerful machine, it's going to take a long time. Now that is dependent on the number of rollouts, right? If I was only doing like 3 rollouts, not expensive. Yeah, you had a hand up?
If they could make the NEA, I feel like very
Sorry, can you say the word? It feels very what?
wonky.
Wonky. So sure, it can lead to weird behaviors from the enemy AI. That's going to be a recurring theme that, like, as you get more complex in terms of the AI that you're using to power your enemy AI, its behaviors are going to get a little bit weirder. We'll get some fun examples on Friday. Yes, Friday we'll have fun examples. Any other thoughts here? Here.
If you're only looking like 1 or 2 steps ahead, can you get stuck?
You can get stuck. Yeah. In fact, the example I was supposed to show you was you getting stuck, but I didn't show you it because I can't read. Did you have a thought here as well? Sure. So that's often intentionally designed, right? This would be overkill, right? If we're talking about little grunt enemies that are supposed to die instantly, like why on earth would you run MCTS for that? For sure, that's reasonable. So I think you've all basically got it, right? It is used. So it is used for some enemy AI, but it's mostly used for enemy AI in complex strategy games with long-term consequences for actions, which is what it's particularly good at representing. And this would be difficult to sort of represent with some of the other sort of more hand-authored methods that we're going to talk about on Friday and next week. Okay? So that's typically the way that it's used. There's particularly some like mobile games online that could do it. It can still select terrible moves. That's certainly true. In terms of the simulate step and automated game playing, right? We were already talking about this. It could be final board quality, number of pieces, etc. In a real-time strategy game, right? We can have score, the number of units, and so on and so forth. Okay, so quick summary, and then there's more time on purpose here. I want to keep 10 minutes because I want to do another example. But a quick summary, and then in terms of what's next. So I want you to know MCTS exists, right? I want you to be familiar with that. I want you to know the major steps here. I also want you to know that when we're using a planning approach, we don't have to think about movement, but actions. This is going to come back up as we hit towards the end of decision making. We're going to get into some really interesting approaches you can use. MCTS is generally overkill, right? Per your point. And on Friday, we're going to cover a much simpler, but I think pretty fun approach that's used instead. That's primarily used these days to handle dialogue in games. And I'll give you some fun examples of that. Okay. And then Monday, we're going to cover FSMs, which is assignment 3. And it's one of the more common approaches. And then on Wednesday, we're going to cover behavior trees, which are the game AI decision-making approach, like of note. They are, if you're seeing a AAA video game, you're seeing behavior driven by behavior trees. That's that. Okay, we have a little more time. So I wanted to work additional examples. And I wanted to particularly work an example where we're not just talking about movement, but we're also talking about actions. Okay? So let's see, can I get away with this? I'm going to try to get away with this, which is to say, just terribly screen sharing this way. So let me end the show. So that way my terrible face and widescreen. Oh no, the video immediately cut out as soon as I ended the show. Wow, Zoom hates me. Look at that. That's ridiculous. Muting's not going to do anything. Why did I mute? What if I choose a video filter? Do we think that's going to fix it? Almost definitely not, right? Gosh, how incredibly annoying. I don't think there's anything I can do. Why does Zoom do this? All right, I'm going to stop my share and I'm gone. I just don't exist. Okay, I'm going to try really, really quickly to get myself into this on my iPad, I guess. When am I doing that? Let's go to participants. Apologies, folks. Just give me a few minutes. Sure, get myself here on a email account. Okay, give me just a few minutes. Yeah, look at that void. What a good example void I managed to put together. Gosh. Okay, turn off Discord. Okay, cool. Yeah. Okay. And now I can share my content. Great. There we go. Okay. Sorry for the weirdness of this setup, folks. Let's talk through a quick example. What is Siddharth saying? We have to remember the watermark for the quiz. This is assignment 3. Yeah, this is assignment 3. Can I get technology to work? Why are you changing to? All right. Okay. Simple environment, right? Let's say that we have a super simple environment that looks something like this. We have an agent. That's our A. We have a boulder, which I'm just going to write as a B, because if I just draw a circle, I mean, I could draw a circle, but like that's not particularly clear what's going on there. So boulder is B, and then we have a goal, G. All right? That's what we're trying to get to. And if I'm trying to get to this goal, I can use something like MCTS. But to know what I can do in MCTS, we have to know what actions are available to me. So let's say that I have 4 actions. I can go up, 5 actions. I can go to the right, I can go down, I can go left, and I can pick up boulder. Okay? So if I'm going to run MCTS from this, this is my root node. The entire thing is my root node. Previously, when we were talking about root nodes, we were talking about it as a particular location on a graph. But in this case, the entire map in this configuration is my root node. Now from here, I can do one of these 5 actions, okay? Just at random. Somebody give me an action. Go ahead. Pick up boulder, I love it. So this edge is called pick up boulder. Let's say that I have a length of 3. So if I pick up boulder, then now my state looks like this. This is why I've done this in such a sort of terribly drawn way, is because I want to be able to do it several times very quickly. So now I'm in a state like this. So if I go to the right from here, right? And if I go to the right again, because I have a length of 2, then I'm going to get to my goal. But it's random. So we're not guaranteed to be able to do that. So let's say that instead I went up, which is going to get me to a state that looks like this. I think that this is going to limit how far I can scroll, which is really annoying. So we're going to have to just sort of deal with this, going slightly off the edge. And then let's say that I go up a second time. So I end up in exactly the same state. Now at this point, we need a measure of goodness here, right? If I'm a state that kind of looks like this, with a reminder that goal is over here, then I could use something like the Manhattan distance, right? But the Manhattan distance isn't going to tell us if the boulder is still there. So in terms of a heuristic for the entire state, we might need to do something like Manhattan distance plus is the boulder picked up or not. So that would be something like 1, 2, 3 plus nothing because the boulder is picked up. So this cost, this right now we think of as being 3 all the way back up to the top. Okay. Let's do it again. In this case, maybe I go up 3 times in a row. And guess what? I would end up in almost the same state, but I never picked up the boulder, right? I would just end up in that top left corner with the boulder still down. So this would be a cost of 4. Now, if I'm using some kind of tree selection policy, so some way of picking which node I'm going to use, that's actually a little bit intelligent, that makes use of some of the information that I've already seen, I'm more likely to go to this one again. And in this case, let's say I do that. Let's say that I do that. And instead of going up, I go to the right from here. Oh, dang, we're getting so close, folks. We're nearly there. But then, unfortunately, I choose to go up. And so I stay in the exact same location. Now, at this point, we're only 1 off from a goal. So this is really good, right? 1, 1, and then we're going to change this from 3 to the average of the 2, which is 2. To be clear, this is from 3 and 1. So one more time, let's say we do one more rollout, and this time I do the correct thing. I go to the right. I found my goal. A is on top of G. The boulder is not there. This is a cost of 0. And we're going to percolate that all the way back up. Now the average of 3, 1, and 0 is 4/3, which, you know, that's like 1 and 1.33333. But that's good enough from there. Now I could keep on rolling this out because there might even be a better way, a shorter path to get there. But right now, in just, you know, a few iterations of this, even though I intentionally took some wrong moves, we can find the answer. And then we can walk this number of actions to be able to find our path, including actions and movement to get to the goal. Any questions on this? Yeah.
So would the one in the middle have a cost of 0.5 then?
Oh, sure. So after this point.
Yeah.
Yes, so I didn't actually back propagate to here. I should have. You're right. It should be 0.5. Anybody else? High level, this is making sense? You feel like you could do something like this on a quiz, for example? All right, some nodding, some confused look. Some people aren't sure what's going on. Some people have been on their laptops the whole time. Let's see. So why are we doing the average again? Because we need some way of representing all the possible things we can get to from here, Sam. This is just one process of doing this. You could also pick the minimum of them. You could have some kind of function to go over them. There's lots of ways you could do this. I'm just doing the average because it's trivial to calculate. Does that make sense? I would specify things like that. I would specify like what tree selection should you be doing? What rollout should you be doing? What's the heuristic at the end look like? What's the back propagation formula? Things like that. Cool. Everybody else good?
So would you use this to get all the way to a goal, or would you use the average to determine just your next move?
It depends on the situation. That's a good question. So we've talked about path planning, right? And we talked about then your goal out of that is a path, right? The output of a path planning algorithm is a path. But we can also talk about, when we're talking about a collection of movements and actions, the output of a planning approach, including both of those, is generally considered a plan. The small difference in how we talk about this. But when we're talking about an entire plan, that is a sequence of actions, including movements and actions, right? Things that we could think of as just moving you through the world and things that are affecting the world in other ways. So we can do both of those things. It depends on the situation. If this is a really giant environment or a dynamic environment, like this is overkill. I do not need to be running MCTS on this, right? There's no reason to. But in a simple enough environment, yeah, we can just return the whole thing, especially if it's static. And then we can just replan if necessary. But in a big environment, you might say like, okay, let's just, let's find one thing that I'm pretty confident is a good move to do next. And I'll just do that. And then I'll reevaluate the next time.
Okay.
Maristella says, do we pick up boulder when we are beside the boulder or on top of the boulder? So this is an implementation thing that I would specify in the question. In this case, I'm assuming if you're next to the boulder, you can pick it up. A is very strong. A is so strong. Of course, I didn't specify the size of the boulder. It could be a small boulder the size of a large boulder. Okay, anything else? We're good? Okay, let's end there. Thank you all. I'll hang out here as per the usual for a few minutes in case there's any questions. Oh.
You open the question one because I don't think about time to like.
Oh, sure.
I don't think a lot of people.
Sure. Whoop. Wait, nope. Whoop. There it is.
Can you not use the given by star
Can you?
I think if I can find the location of the parent node and the parent location, we can use the unity distance.
Sure. There are multiple ways to solve this problem, is what I'll say.
Okay.
You don't need to go searching for like one way to do it. There are many ways to get around it. All right, I think that's it from the Zoom folks. I'm just going to go ahead and close it.